Very good morning to everyone. So, we were looking into the applications of eigenvalues and eigenvectors in various chemical engineering problems. So, in the last few classes, we have looked into the solution of solution of the set of algebraic equations, set of ordinary differential equations, and homogeneous and non-homogeneous equations. Those will be arising out of the chemical engineering processes, and how eigenvalues and eigenvector method can be applied quite elegantly and replacing the numerical techniques, and including involving, even if you go for a higher dimensional operation, the numerically calculated values will be done quite easily, involving very small subroutine of elementary nature. Now, what we have seen in the earlier classes, that we have developed the theory based on this to solve the set of algebraic equations and ordinary differential equations, both homogeneous form and non-homogeneous form, and along with that we have discussed some of the problems, how to apply the eigenvalue eigenvector method for their solution. Now, in today's class we will look into another application of eigenvalues and eigenvectors that will be appearing in the continuous domain. So, we will be looking into the stability analysis of any chemical engineering processes. This stability is very important as far as the chemical reaction engineering and chemical engineering processes are concerned, because consider any chemical reactor, if it is operating under the stable operating conditions, then you can ensure the quality of the product you are going to get. So, if the quality of the product is ensured, then its marketability and market value will be ensured. So, we can do a very good business. If the stability of the system is not appropriate, then one cannot be very sure about the product quality. So, stability analysis is very important. So, we will be basically looking into the various theorems what will be applicable for analyzing the stability of any chemical engineering processes, and after that we will be doing the analysis based on this theory and trying to extract the features or the set of operating conditions under which the operation can be carried out under stable conditions. So, stability is very important as far as the chemical engineering processes, and whatever we will be doing from today's class onwards, that will be extremely important for the chemical engineers to analyze the stability of a system. So, let us look into the various methods involving eigenvalues and eigenvectors, and we will develop the theory for the stability analysis. Now, if you look into the solution, if you look into the solution that we have talking about, that the solution of a system, of a linear system, even it is valid for the nonlinear system as well. Solution of a linear system will be in time domain is in the form of e to the power lambda t, where typically the lambdas are eigenvalues of the relevant problem. Now, this lambda this lambda can be positive, it can be negative, it can be even 0, it can be imaginary. If it is imaginary, then of course, its counter the conjugate will be appearing. So, if there are two roots, then there is a possibility of having imaginary roots. Now, there is we can see in this problem that if depending on the sign of lambda, the response can grow in time or recede in time. That means, if lambda is positive, then e to the power lambda t is ever increasing function. On the other hand, if lambda is negative, then e to the power minus lambda t is ever decreasing function. If lambda is imaginary, let us say p plus minus I q, then e to the power, this will be entirely depending upon the real part of lambda. Now, if real part of lambda is greater than 0, then the response will grow in time. If real part of lambda is negative, the response will die down in time. So, if e to the power lambda is positive, if it is e to the power lambda t is ever increasing function, that means, if you put a disturbance in a system, it will grow in time monotonically. On the other hand, if we put a disturbance in a system for lambda is negative, the response will die down in time. So, therefore, for in case of imaginary roots, it entirely depends on the real part of the root. If root is positive, then the disturbance will grow in time. If this real part is negative, then the disturbance will die down or decay in time. Now, this will be extremely important as far as the stability of the system is concerned, that if you impart a disturbance in the system, if the response grow in time, then we are basically landing up into a system which is not stable. On the other hand, if the response decays with time, then we will be landing up in a system which will be stable. So, the aim will be to have a stable region. So, there will be conditions that this eigenvalue will be negative, then we will be getting into the into a stable region, and of course, that will happen under a certain combination of the parameters, where the parameters are basically a combination of operating variables. So, under those operating variables, so that they will satisfy those conditions, the system will be operating under stable steady state. Now, in order to develop the theory, we will just take up a chemical engineering application, and we will take up whatever we have done earlier, that is in case of contraction mapping, we will take up an example of continuous start tank reactor, which was non-isothermal. So, we take up those conditions of the energy balance, those equations of energy balance and mass balance to start up with our discussion in the context of stability of chemical engineering processes. Now, let us consider the CSTR problem, whatever we have developed discussed in case of contraction mapping. Our CSTR problem, we have the solute mass balance was given by dC dt is equal to minus C plus dA 1 minus C e to the power t. This is nothing but solute balance, and dt dt is be given by minus 1 plus beta t plus b times dA 1 minus C e to the power t. So, this will be the heat balance equation. Okay. The parameters in a system are Damkohler number, beta is a non-dimensional parameter, and B is another non-dimensional parameter. Now, these three are the parameters of the system. Now, let us look into the steady state of this system. The steady states will occur when this time derivative will be equal to will be forced to equal to 0. So, the steady state will be occurring by putting 0 is minus C plus dA 1 minus C e to the power t. This is equation 1a and minus 1 plus beta t plus b dA 1 minus C e to the power t. So, this is equation 1b. So, we have already seen that by contraction mapping if b is less than 4 into 1 plus beta, then we will be having unique steady state for this particular problem. So, we have already seen by contraction mapping that if b is less than 4 into 1 plus beta, unique steady state exists. So, we can combine equation 1a and 1b and we can write dA is equal to C 1 minus C e to the power minus b divided by 1 plus beta times C. So, this will be a function of concentration only. So, if we plot dA or f of C as a function of C, we can see that it will be an ever increasing function. Now, if this is the case, then if we have f c is a monotonically increasing function with increasing with C, then we have unique steady state corresponding to a dA to a Damkohler number and a stable solution is obtained. This we have proved earlier during the discussion of contraction mapping, that if f c is monotonically increasing function with concentration, then for those particular dA Damkohler number we will be getting the stable steady state. On the other hand, if f c is not monotonically increasing, then we will be landing up with multiple steady state. That means, if f of c is not monotonically increasing, then we may land up with multiple solution or multiple steady state. That means, if we plot dA f of c, dA is same as f of c versus concentration. If the plot looks something like this, it is not monotonically increasing function, it is decreasing and then again it is increasing, then you will be having a particular dA may be here intermediate, where there will be a solution here, there will be a solution there, there will be a solution there. So, there will be 3 solutions may coexist, they may exist. So, you can have the upper limit. So, if this is the case, then you will be having the upper Damkohler number dAu, and this will be you will be getting a lower Damkohler number dAl. So, there will be a Damkohler number in between dAl and dA upper, for which one can have a more than one solution or more than one steady state. So, between this limit dAl and dAu, one can have multiple steady state of this particular problem. So, of course, so what we can understand from this discussion is that in order to have existence of multiple steady state, the f c will be having a maxima and will be having a minima. Then only if the function of concentration will be having a maxima and minima, then only one can expect of occurrence of multiple steady state. Now, let us put this condition in this particular case. So, for multiple steady state, F C must have a maxima and a minima. So, f of c should be equal to c divided by 1 minus c e to the power minus b c divided by 1 plus beta. So, in order to have a maxima or minima, let us get a differentiation of this. So, this becomes 1 plus beta minus b c into 1 minus c divided by 1 minus c square into 1 plus beta e to the power minus b c divided by 1 plus beta. So, so this is the differentiation of f of c. So, I am just writing the final expression. So, for maxima or minima, f prime c will be equal to 0. So, therefore, one can get this equation b c square. So, if this will be basically the numerator will be equal to 0. So, it will be 1 plus beta minus b c plus b c square is equal to 0. So, you will be having condition b c square minus b c plus 1 plus beta is equal to 0. Now, this will be having two roots. This is a quadratic in C. So, it will be having two roots. So, let us find out what these two roots are. They will be minus b. So, it will be plus under root b square minus 4 a c. So, b times 1 plus beta divided by 2 a, that means 2 b. So, if we take b common from here, so what we will be getting is that 1 by 2 1 plus minus under root 1 minus 4 into 1 plus beta divided by b. So, that is the so there are two roots. One root corresponds to maxima and other root corresponds to minima. So, these two roots correspond to maxima and one for minima. Okay. So, now we can have now in order to have a real solution, we can have the condition on this part that this 1 minus this part should be greater than 0 in order to have a real root or real solution. So, let us do that. For real root, the quantity within the under root sign must be greater than 0. So, therefore, 1 minus 4 into 1 plus beta divided by b should be greater than 0. So, therefore, 4 into 1 plus beta divided by b should be less than 1. So, we will be having b is greater than 4 into 1 plus beta. So, this is the condition for this particular problem in order to have a multiple steady state. So, this becomes the condition to have multiple steady state of this problem. This is just a counterpart of whatever we have obtained for the condition of having the unique steady state of this problem. So, if you remember that the condition we obtained from contraction mapping for existence of a unique steady state is b less than 4 into 1 plus beta. So, obviously, when b is greater than 4 into 1 plus beta, that is the condition for the multiple steady state, and we have derived that. So, now if you plot C versus Damn-Coulomb number versus C, or C versus Damn-Coulomb number, whatever way. So, these will be there may be one response like this, there may be a response like this. So, this is in this case for every C you will be having only, for every Damn-Coulomb number you will be having only one C. For this curve for the lower curve, for every existence of Damn-Coulomb number you will be getting only one concentration, one solution, steady state solution, and therefore, on this curve the unique steady state exists. So, B is less than 4 into 1 plus beta. On the other hand, if you talk about this range of Damkohler number, for this Damkohler number, any Damkohler number between dA upper and dA lower, there will be having 3 steady state or multiple steady state existing for this problem. Any Damkohler number beyond dAu will be leading to a steady state on the upper branch. Any Damkohler number below the value of dAl, one will be getting a solution at the lower branch. For any Damkohler number lying in between dAu and dAl, it will be having a multiple steady state in the system. So, if we plot now for this particular problem, if we plot now T or C versus Damkohler number for multiple steady state part, you will be getting a curve like this. This is the condition for B greater than 4 into 1 plus beta. So, if we summarize whatever we have obtained in the earlier slide, that this is for this case B is greater than 4 into 1 plus beta. That means, this is for condition for unique steady state, and this is the condition for multiple steady state. Okay. So, next we have the T and C versus Damkohler number for the condition B greater than 4 into 1 plus beta. This is known as upper steady state branch, and this is the lower steady state branch. Now, suppose this is dAi. So, if dAi increases slightly, both T and C they jump on the upper steady state branch. Therefore, dAi is called an ignition point. So, if you just slightly increase, it is beyond dAi, it will go to the upper steady state branch. So, dAi is called the ignition point. On the other hand, the other limit is dAe. dAe, if we slightly decrease dAe, if dAe is decreased slightly, then T or C they jump on lower steady state branch. So, dAe is known as extinction point. Okay. So, which steady state will be if in between the dAe and dAi, if we operate on any Damkohler number, we will be having a multiple steady state. Now, for dA lying in between dAe and dAi, which steady state is obtained, that will be entirely depend on the initial values of T and C. Which steady state among multiple? That is the question. Then it entirely depends on initial values of C and T. So, depending on the initial value of C and T, one can get a the steady state in between. Now, next we talk about all these phenomena can be properly explained if we talk about a phase plane plot. So, let us look into the phase plane plot. So, first let us define what is a phase plane. Suppose any system is defined by two ordinary differential equations like dx1 dt is function of x1 and x2, x1 x2 are the state variable, dx2 dt is equal to g of x1 and x2. Then the plane where the system behavior evolves dynamically, the variation of x1 and x2 is called a phase plane plot. Plot of x1 and x2 is known as phase plane plot. So, if we plot x1 as a function of x2, it gives a plane in which system behavior evolves dynamically. Now, in this case time is a parameter. Okay. So, that gives a concept of phase plane plot. Now, let us look into some more concepts and definitions. First one is the repeller. So, let us see what a repeller is. Repeller is a steady state. It is a steady state around which if you have any initial condition that will lead to a divergence from the steady state. It is a steady state around which any initial condition leads to divergence from steady state. So, in the earlier example dAI is a repeller. So, if we have any steady state about that point, then it will either go to the upper steady state or it will go to a lower steady state. Then attractor, this is a steady state around which any initial condition leads to that steady state. So, that steady state is called an attractor. So, steady state, this attractor may be in the earlier example any steady state sitting on upper branch or lower branch is an attractor, and dAI or dI in the earlier example is a repeller. So, any steady state around dAI either it will be landing on upper steady state branch or lower steady state branch. On the other hand, if any steady state is sitting on the upper or lower branch beyond the DAI and DAE region, that will be acting as an attractor. Now, let us try to develop the theory of stability for a two-dimensional system. This can be extended for a multi-dimensional system. So, for that we consider a two-dimensional autonomous system. Consider a two-dimensional autonomous system, and autonomous system means independent parameters do not appear explicitly. If independent parameter does not appear explicitly, then we call that system as autonomous system. For example, if the state variables are x1, dependent variables are x1 and xt and x1 and x2, and the independent variable is dt. If it is 2x square x1 square minus 3x2 plus 5, and if dx2 dt is equal to 5x1 minus 3x2 square plus let us say 6. Now, this system is an autonomous system because the independent variable t does not appear on the right hand side in either of the equation. So, this is an autonomous system. Now, let us consider an autonomous system where x1 dot is equal to dx1 dt, and in general this will be a function of x1 and x2, and in the second case second equation x2 dot is dx2 dt is equal to another function of x1 and x2. So, it does not, the right hand function f1 and f2 are not functions of x1, x2 and t explicitly. So, that is why they are called autonomous system. Now, most of the chemical engineering processes, they fall under the category of autonomous system. Now, let us look into the steady state solution of these two equations. So, the steady states are 0 f1 x1 s s comma x2 s s, s s stands for the steady state, and 0 is equal to f2 x1 s s and x2 s s. Now, let us consider a deviation about the steady state. Consider a deviation about the steady state, and these deviations are x1 hat is nothing but x1 minus x s s, and x2 hat is x2 minus x s s. Now, in order to evaluate the now what we are going to do, we are going to do the evolution the dynamics of the deviation variable. So, these are called deviation variables of the two independent variables x1 and x2. This will be x1 minus x1 steady state, x2 minus x2 steady state. So, to evaluate, we evaluate deviation dynamics. How to evaluate that? We evaluate all the governing, we write all the governing equations in terms of x1 hat and x2 hat. So, therefore, we can write these two equations as dx1 hat dt. In fact, if we differentiate this equation with respect to t, dx1 dt is identical to dx1 hat dt. So, this will be nothing but function f1 x1 hat plus x1 ss and x2 hat plus x2 ss, and similarly we have dx2 hat dt is equal to f of 2 x2 hat plus x2 ss and x1 hat plus x1 ss. Now, so we express the all the parameters the dependent variable x1 and x2 in terms of deviation variable x1 hat and x2 hat. So, next we linearize the problem about the steady state. Next step is linearization about the steady state. If we do a linearization, then x1 dx1 hat dt or x1 hat dot becomes f1 x1 ss and x2 ss plus del f1 del x1 x1 minus x1 ss plus del f2 del f1 del f1 del x2 x2 minus x2 ss. We give a slight deviation about the steady state by test. So, we linearize this thing by Taylor series expansion and retain the only the first term of the expansion, and these derivatives are about the steady state, these very derivatives about the steady state. So, we retain the first term of Taylor series expansion and delete the higher order terms, because the deviations are extremely small compared to the steady state. So, therefore, we can write dx1 hat dt will be nothing but f1 x1 ss and x2 ss plus del f1 del x1 about the steady state x1 hat plus del f1 del x2 at the steady state, this will be x2 hat. So, that will be the governing equation of dx1 hat, the deviation variable, the dynamics of deviation variable by using linearization, and that linearization will be restricted to up to the first term and neglecting the higher order terms of Taylor series expansion. Similarly, we will be getting the next part of the deviation variable dx2 hat dt will be nothing but f2 x1 ss x2 ss plus del f2 del x1, and that will be evaluated as steady state, and this will be x1 hat plus del f2 del x2 evaluated at the steady state, and that will be multiplied by the x2 hat. So, therefore, what we can do, we can write these two equation in a compact form, and also if you remember that f1 x7 ss and x2 ss were equal to 0, and f2 both f1 and f2 evaluated at steady state, they are equal to 0. If you look into the earlier slide, that these were the governing equation of the system we are considering, and at the steady state these will be equal to 0, and f1 x1 ss x2 ss equal to 0, and f2 x1 ss x2 ss will be equal to 0. So, therefore, we have every right to make these two equal to 0. So, the neat at compact form will be dx1 hat dt, in the deviation variables will be del f1 del x1 evaluated at steady state x1 hat plus del f1 del x2 evaluated at steady state x2 hat, and dx2 hat dt will be nothing but del f2 del x1 steady state x1 hat plus del f2 del x2 steady state x2 hat. So, these two equations in the deviation variable can be written in a compact matrix form as dx hat dt is equal to j times x hat, where x hat is nothing but a matrix, a vector which will be having two elements x 1 hat and x 2 hat and transpose of that. So, it is nothing but a vector x 1 hat and x 2 hat, and the Jacobian matrix J becomes the elements of the derivative. They will constitute the derivatives will constitute the elements of the Jacobian matrix, and these will be del f 1 del x 1 del f 1 del x 2 del f 2 del x 1 and del f 2 del x 2, and all these derivatives which are the elements of the Jacobian matrix, they will be evaluated at the steady state. So, the solution of this equation will be in this form of x hat t will be is equal to C 1 u 1 e to the power lambda 1 t plus C 2 u 2 e to the power lambda 2 t, because it is 2 into 2 matrix. So, we will be having a two eigenvalues lambda 1 and lambda 2, and u 1 and u 2 are I corresponding eigenvectors. So, stability of the perturbation, this disturbance value variable is nothing but the perturbation variable. The solution or stability of perturbed variable or the perturbation that we have imposed from outside, they will be entirely depend on sign of real values of lambda I. So, real values of eigenvalues will dictate whether this the perturbation variable will grow in time or it will die down with time. So, if real value of lambda is positive, then this even if one of them is positive, the whole solution, the disturbance variable will grow in time. If it is negative, then if all of them will be negative, then it will be stable solution and the perturbed variable will die down with respect to time. So, the sufficient condition for instability is condition for instability is real value of lambda I should be greater than 0. So, for at least one lambda I, then if that means if in a system there are 4 or 5 eigenvalues, if the real part of one eigenvalue is greater than 0, the system becomes unstable, and that will be the sufficient condition for the instability. We do not require any more condition to check the instability. If one of the eigenvalues will be having a real part above 0, greater than 0, positive, then we will be having an unstable solution. Next, we will look into some of the definitions. First one is called a trajectory. Trajectory is a curve generated in a phase plane, that is called a trajectory. It has a direction starting with the initial value. it has a direction and the starting point is the initial value. Okay. Now, next we classify the various steady state. So, classification of steady states, these are quite important, and you come across of several terms later on, that is the unstable saddle, unstable node, focus, stable focus, unstable focus, so on and so forth. So, let us classify the steady states. The first classification is the unstable nodes. If two eigenvalues are positive, unstable nodes occurs that when two eigenvalues are positive. And the phase plane plot looks something like this. So, you will be having an initial condition here, then okay. So, any deviation about the initial condition, it will diverge from this steady state, and this node is called an unstable nodes, and these will be the direction of the eigenvectors. The tangential directions presented in the node are the eigenvectors. So, therefore, trajectories diverge from the steady state monotonically. So, that is the feature of unstable node. Okay. So, u1, u2 are the eigenvectors. So, these are the direction of the eigenvectors. u1, u2 are eigenvectors which are tangent to the at the steady state. Such kind of node or steady state is called unstable node. So, because of the presence of unstable node, any steady state around this point will diverge from this steady state. So, these are called unstable nodes. Then we talk about a stable node, that is the second type of steady state. Stable node is this: at this steady state, both eigenvalues are negative. So, lambda 1 is negative and as well as lambda 2 is negative. So, that means the trajectories converge to the steady state. In phase plane from all direction. Then that particular node is called stable node, and if you look into the phase plane plot, so it will be x1 versus x2, and if this is the steady state, any steady state around this point will converge to this. So, which steady state, now suppose A, B, C, D, now which trajectory it will follow. Suppose you have a steady state here and you have a point around the steady state. From this point Now, it will be following this. Now, based on the condition, based on the initial condition, it will decide which steady state, which path it will take up. So, based on initial condition, based on the initial conditions, the path A, B, C or D will be selected. So, that is called a stable node. That means, in case of stable node, we can have where we have the eigenvalues less than 0. That means, both of the eigenvalues are negative and one can have a very stable system around that point. So, any deviation about the steady state will lead to the particular steady state. So, then it is called a stable node. In case of a system where one of the eigenvalues is positive, then you will be having the any deviation from the steady state will lead to divergence from that particular solution. If all steady states are, if all eigenvalues are positive, then that will be an unstable steady state. So, it will be that will be an unstable node. So, any deviation from any direction of the steady state, it will diverge from the steady state. Next, we will in the next class, I will stop in here at this class. In the next class, we will look into some more definitions of the steady state, and we will complete the classification of the steady state. Then we go to the appropriate examples and further develop the theory, and finally, we will take up some of the examples of chemical engineering system. Thank you very much.